Wow, oh my, how the time flies. We are already on our fifth and last parametric lesson, and this will be I guess it's a very ceremonial lesson in the sense. This will be our last new lesson for our course, and it's been quite a journey, and now the real race begins as we rally for May 8th. But so we're going to talk about motion along a curve today. We're talking about two-dimensional motion, and here's a really nice free response question to get the party started, and we'll break it into smaller pieces as we get going. But I wanted to just, terminology wise, the test development committee calls this part the stem of the question, okay, and that's not a big deal. But what I do want you to know, my point is, when you see an equation in the stem, that typically means you're going to use that equation repeatedly throughout the question. And so one of the things I like to do is I like to instantly go write those equations in my y1s, in my y2s, knowing that I'm going to use them repeatedly, and I think that'll save time in the long run. So for part A, all they want is the acceleration vector. Now keep in mind that you do know the velocity vector already. They said that the velocity vector, and I'll just rewrite it with a little different notation here. They said the velocity vector is sine of t cubed and then the cosine of t squared, okay? And so that means the acceleration vector is simply, with a little bit of chain rule, we've got, let's see, 3t squared cosine of t cubed. And then we've got negative 2t sine of t squared. And then we're going to evaluate that vector at 2. So essentially we've got, was that 12 cosine of 8, comma, negative 4 sine of 4. And we'll throw in the calculator around to 3 decimals. Now, the alternative is, and I'd even like to see you skip all of this work by hand, okay? But you could make the argument that this one, the derivative was simple enough that you could do it by hand. I'd like to see you go straight to the calculator and since this is already in y1, tell the calculator to take the derivative of y1 and evaluate it at 2, and here's what your screen would look like. So the first picture here on the left is just me emphasizing to go, right away, before you even read part A, just go get those equations in y1 and in y2, make sure we're in radian mode. But then here's what my screen would look like. Of course, I've got the updated TI-83, and this is what my screen looks like. Remember, if there's that quick grab option for y1 and y2, right here, if you want to grab y1 really quick, instead of going to like the vars menu and sorting through all that, if you just go alpha F4, I'll put a little note here, alpha F4, there'll be a quick grab shortcut for y1 and y2. And those are I'm going to use 3 decimals here for my 2 answers, and that will be my acceleration vector. Now, how will I express my final answer? I would write it just like this. I would say A of 2, with that vector notation, negative 1.746, and then 3.027. Good notation, just like that. Okay, part B. They're asking for the equation of a tangent line to the curve at the point where t equals 2. Here's the good news. Back there in the stem of the question, they said when t equals 2, the position is 1, 4. So the good news, you already know your x and your y coordinate. The only thing that's missing is slope. So we know that dy dx is really dy dt divided by dx dt. And let's see, your dy dt is going to be, they gave us cosine of t squared, and then the sine of t cubed for dx dt. And then all we're going to do is we're going to evaluate that rascal at t equals 2. So now we've got the cosine of 4 divided by the sine of 8. Throw that bear in your calculator, and you should get negative 0.661. There's your slope. So we'll put it all together. We could say y minus 4 equals negative 0.661. quantity x minus 1, and certainly it's my understanding that you don't even actually have to plug that part into your calculator. If you just substituted that fraction in for the negative 0.661, you should still get full credit. And anyway, that's your tangent line. Alright, they threw one of our new buzzwords at us. They're talking about speed here, and they wanted the speed specifically at the moment when t equals 2, and speed is certainly, all that is the magnitude of the velocity vector. In other words, what's the length of the velocity vector? And if you really think of it as length, all right, and anytime you think of length, you should be thinking of the Pythagorean theorem. I think that's going to help you remember this obscure formula. All it is the square root of dx dt squared plus dy dt squared. So all you do is just imagine the Pythagorean theorem and then solve for c, and you've got to basically the speed formula. Then what we're going to do is we're going to evaluate this rascal at t equals 2. So what we've got is the sine of 8 getting squared, and then the cosine of 4 getting squared, and that turns out to be 1.186, and that's a real nice straightforward one to throw in your calculator. The biggest news is just, hey, recognizing what speed is implying and getting this beautiful formula memorized. Recall that this formula is the same thing as the total distance traveled or arc length, just we don't have the integral in front of it anymore. Our last one, part D, might be the most challenging, but I don't think it's too bad. They want us to find the position of the particle, specifically when t equals 1. Keep in mind, you already know that when t equals 2, the x-coordinate is 1 and the y-coordinate is 4. This is definitely a two-part question. We're going to attack the x-coordinate first, then we'll attack the y-coordinate second, and we're going to use the first fundamental theorem for both of these. That's a fundamental theorem's really come in handy lately. And so what I'm going to say is let's integrate dx dt, that function, with respect to time. Let's see. I want to know t equals 1. They gave me t equals 2. Those are the two time values that are in play. That will give me the position at 2 minus the position at 1. Let's see here. Now, I'm actually solving for the position at 1. That's what I'm solving for. So I'm going to add that quantity to the other side, and then I'll subtract the integral over. And then the calculator is really going to come in handy here. We've got a definite integral that I can simply throw into that calculator. So it's going to, and we know that x of 2 is just equal to 1. So it's going to be 1 minus whatever that integral is. And when I threw that into my calculator, I got 0.782. That was the x-coordinate when t equaled 1. So we're halfway home right now. We're halfway home. I'm going to pick a different color here. We'll start all over. Let's talk about the y value. We know that if we integrate from 1 to 2, dy dt, we'll get the y position at 2 minus the y position at 1. Again, we're looking for y sub 1, so we'll add that bear to the other side, and then we'll subtract our integral. And let's see, what do we know? We know that y of 2 is a 4, and then we'll throw the definite integral into the calculator. So I ended up getting 4.443 for the y-coordinate. If we put this all together, we could say that the position is 0.782, 4.443. Bingo, there it is. So first fundamental theorem, good friend of ours, and we're really wrapping up these parametrics. We're doing well, and this is certainly a topic we want to be able to dominate on the exam. When we see this free response question, this is one that we really need to get 9 out of 9 on. This and the area volume problems are always the highest scoring questions, and we need to stay ahead of the curve.